Okay, so this talk is titled The IPS Compiler and Related Constructions. This title was chosen by the organizers for me. A more title that better reflects the contents of the talk is perhaps Related Constructions and the IPS Compiler. So I'll start by Related Constructions and then get to the IPS Compiler. Okay, so let's again go back in time to the 1980s. We have, for some reason, okay. Yuda, do you know how I can make the
Where's the mouse? Just turn it off and let's start again. No. There you go. You had two open, okay. That's why. You have to close this one first. Oops. Where is it? I closed it by accident. IPS. Yeah, the other one's still open, so just check this one.
Okay, great. Thanks, Yuda. Okay, so I'll talk about the IPS compiler and the related constructions. So going back to the 80s, we had, I think, four major and very distinct feasibility results that are relevant to secure computation. The first is a beautiful concept and of zero knowledge and the fact that we have general zero knowledge for NP. Then we had the result of Yao and GMW that showed how to apply zero knowledge to get computational MPC in the setting of no honest majority. Then we had two unconditional results. The better known is the one by BGW, CCD, and Rabin and Benor that showed unconditional security with honest majority. And finally, we had the result by Kilian that showed that actually Kilian showed it in the two-party setting, that if you have an ideal oblivious transfer, then you can also get unconditional security in the case of no honest majority. And the natural question, all these are very, heavy results that use very different techniques. And the question is whether they're really unrelated or we can find some redundancy here. Whether some of these results can be thought of as being implied by others. And the general message of this talk is that, yes, there is such a relation. We can use honest majority MPC even in the case where we have no honest majority. So for this talk, no honest majority will almost entirely refer to the two-party case. So this is a picture you can have in mind of two parties that interact with each other, and in their head they run some multi-party protocol. This type of connection gives us, or actually a couple of connections I will show, gives us some unexpected relations between these classical results that I mentioned, and are also useful to get new results in the case of for secure computation in the setting of no honest majority. So in this talk I will not have a lot of time to discuss applications, but you can actually, or we could actually get new theorems that talk not only about asymptotic efficiency, but also about certain black box feasibility results that were not known before and were obtained by exploiting results that were known in the context of honest majority and exporting them to the setting of no honest majority. Okay, so these are the two PhD students that some of you know, and unfortunately they couldn't make it here. Those are among the few that didn't make it here. Their names are Alison and Bernard. For those that don't know them, Alison, she's from MIT, and she's interested in zero-knowledge proofs and efficient protocols for secure two-party computation. And Bernard, I'm not sure how to pronounce his name, he's from the University of Yuval, and he's interested in information theoretic cryptography and in honest majority MPC. And these two guys, they don't really know each other, but if you look at what they're interested in, you can think of Alison's techniques as being relevant to Bernard. So if you think about, even in the previous talk that I talked about information theoretic cryptography, I used the concept of zero-knowledge proofs. You can think of applying, in the context of honest majority, of applying techniques from two-party cryptography. This has been done, for instance, in the GMW paper, right? They have a result for the honest majority case with guaranteed output delivery. So we've seen quite a few instances of relevance of Alison's techniques to Bernard's world, but in the other direction, this is much less common. And so if Bernard were to approach Alison and try to get her interested in his research, this will probably not be a good basis for a relationship. So let's try to make the match. And so one natural idea for making the match is to add to Alison's world a simple ideal functionality that in some sense captures what she wants to achieve, or at least some minimal primitive for what she wants to achieve. So if Alison is interested in zero knowledge, let's allow her to use an ideal commitment oracle, which is exactly what it sounds, right? This is the ideal functionality that directly captures commitment. And we'll refer to this as the COM hybrid model, right? It's a hybrid model, a model where the parties, the computation, is aided by some ideal functionality oracle. In the case of general two-party protocols, we can add an ideal oblivious transfer oracle. Again, just a reminder, oblivious transfer is a functionality that takes two strings from a sender, one bit from a receiver, and gives the selected string to the receiver. And now, in these hybrid models, unconditional and even UC security becomes possible. This is analogous. Even in Bernard's world, he needs some kind of hybrid model, namely secure point-to-point channels. And this basically brings unconditional security to the two-party world. Now, okay, that's good. That's a way to bring unconditional security to Alison's world, but why should Alison be happy? She thinks of unconditional security as being uncool, right? So why would she want to use this abstraction of an ideal oracle and design unconditional protocols relative to this oracle? So this has several advantages. One is generality. If your protocol is unconditional in the hybrid model, you don't need to base it on DDH or on pairings or any other specific assumption. Then you can use, then you can realize this oracle in a variety of ways under a variety of assumptions, a variety of models. You don't need to redo the analysis and the design whenever you want to have some new implementation of your protocol or use it based on a new assumption. The other motivation has to do more specifically. The first motivation is broad and in general applies to this modular design principle. The second motivation has more to do with the specifics of these two simple functionalities. So both of these functionalities, commitment and OT, they can be realized efficiently, and even more so if you allow preprocessing and amortization. So we've heard from Benny yesterday about the efficiency of oblivious transfer. And a nice point about oblivious transfer is that it's a random self-reducible in the sense that you can offline run an oblivious transfer protocol on random inputs, and then online, similarly to using a one-time pad for encryption, you can online just send corrections and get a super efficient online protocol for oblivious transfer. And this offline phase, again, something that Benny mentioned, could be made more efficient by techniques for amortizing the cost of oblivious transfer. And of course, the main bulk of Benny's talk was to make the case that even if you don't use preprocessing and don't use amortization, then oblivious transfer is not so bad. Today, or in recent years, we have several efficient protocols that we heard about yesterday. So, okay, so that's very good, but I still didn't answer the question I started with. Why should so we brought unconditional security to Ellison's world, but we still didn't justify the relevance of the honest majority setting or the multi-party setting, and this is what this talk is about. And the high-level idea, as the previous picture illustrated, is to run some MPC protocol in the head, to have, this is just some, we will see two flavors of this idea. This captures more or less the first flavor. We'll see a more complicated version in the second part of the talk. But very broadly, we kind of run the MPC protocol virtually in the head. We make some form of a commitment to the views we generated, and then we apply some form of consistency checks to ensure that indeed there is an honest majority in the views that we're committed to. So that's a very high-level idea, and we'll start by a relatively simple application of this idea to the case of zero-knowledge proofs, which again, as we heard in Benny's talk on Sunday, even if you want to do general secure computation, getting good zero-knowledge proofs, we heard it also from Yuda yesterday, getting good zero-knowledge proofs is very useful. Okay, so we're now in the setting that Yuda defined formally yesterday. We have an NP relation R. It's some efficiently computable function that takes an input X and a witness W. And we want to use a honest majority multi-party computation for designing a zero-knowledge proof for the relation R in the commitment hybrid model. Okay, so if we want to use an MPC protocol, we'd better first say which functionality this protocol is for. Right, so our functionality, which we will denote by G, it will take the input X as a public input, right? It's something that everybody knows. You can think of this X as being a part of the description of the functionality. And now the main point is that every party will have a private input Wi that has the same length as the witness. And the functionality will first compute the exclusive OR of all these inputs Wi, and then output the verdict of the verification relation. So 1 for pass, 0 for fail. Okay, that's a concrete multi-party functionality that is defined by the zero-knowledge relation R. And what I would like to show now is a very simple way for taking a protocol for this functionality in a very benign adversarial setting and using it to get zero knowledge. So the specifics of the protocol, we want it to be secure in the semi-honest model against two corrupted parties. And in the variant that I will describe now, we also want correctness to be perfect. Privacy can be, can be perfect, statistical or computational. But for the first variant I will describe, it's crucial that the protocol will always return a correct output regardless of the choice of the randomness. Okay, and so if we want to use honest majority NPC, we are free to choose whatever n we like, so we can let n be 5 and use the simple BGW protocol in the semi-honest model that Benny described. Okay, so how does the zero knowledge protocol work? This is a reminder of how our functionality G looks like that were implemented via the MPC. So the prover starts with the witness W, right? What the prover does is additively share W into n shares. Recall that n is the number of parties. And now each of these shares will be viewed as an input to the corresponding party in the MPC protocol. Okay, now the prover will run the MPC protocol pi in its head. This execution generates a view for every player. Right? You can think without loss of generality of a view as containing the randomness, the private input, and the incoming messages. Right? The outgoing messages are determined by this information. So the prover will commit to each of these views separately. Right? And this is the information that will be received by the verifier. He will get an ideal commitment to each of these views separately. Now, what does the verifier do? The verifier wants to make sure that indeed the views are consistent and that the output of the parties is a 1, because a 1 corresponds to these inputs being shares of a valid witness. So the verifier will challenge the prover with a pair of random views. The prover will open the corresponding commitments, and the verifier now checks two things. First of all, that the output reported in these views or implicit in these views is indeed 1. And the second thing to check is that the views are consistent in the sense that the incoming messages reported in one view are the same as the outgoing messages that are implicit in the other view. Okay? Or you can include both incoming and outgoing messages in the view, and then you need to check that the incoming and outgoing are consistent with the protocol. Anyway, you check all the consistency checks that you make, and accept if both the output and 1 and this consistency check is met. Okay, so now the claim is that this works. Let's separately argue. So completeness is easy because it follows from the correctness of the MPC protocol that the output will be 1, and if the prover faithfully runs the protocol, then all consistency checks will pass. Now the zero knowledge basically follows from the two security of the MPC protocol and the randomness of these shares of the witness. So the MPC simulator needs to get the inputs of the corrupted parties, but because these Wi and Wj are completely random and independent, we can feed the MPC simulator with these random strings. And note that it is enough to use, even if we have n players, we can just take inputs from 3 of them. Right? We don't need all of them to have inputs. The more interesting argument is for soundness. Now, let's assume that X is such that it has no witness. In such a case, we should make sure that there is no way for the prover to convince the verifier to make the verifier accept with high probability. So here we divide into two cases. We divide the prover strategies into two cases. The first case is that the views that he generated are consistent with some valid execution of the MPC protocol. The second case is that they're not. Okay, and let's see that in each of these cases, the verifier will reject with some significant probability. So in the first case, because there is no W that the prover can choose, there are no Wi's that will make the correct execution of the MPC protocol output 1, then the outputs of the MPC will be 0, and then the verifier will always reject regardless of the players that he picks. In the second case, and this again requires a formal proof but can be proved easily by induction on the number of rounds, if the views are not consistent with any execution of the protocol, then there must be at least one pair of inconsistent views. Right? It's easier to prove the converse, that if all pairs are consistent, then they're globally consistent with some execution. Right? So in this case, in the worst case scenario that there is one pair of inconsistent views, the verifier, in the event that the verifier will open the inconsistent pair, he will reject, and this will open with at least 1 over n squared or 1 over n choose 2 probability. And when n is constant, this will be a constant, or even if it's non-constant, we can amplify this by repetition. Okay, that's good. And in fact, even the stronger proof of knowledge property that Yuda mentioned in his talk is satisfied by this basic approach. Okay, in terms of complexity, because we're only making a very simple and black box use of the MPC protocol, the efficiency of this zero knowledge proof in the commitment hybrid model will be essentially the same as the MPC protocol. So the amount of communication involved in opening the views is bounded by communication complexity and randomness complexity and input size of the MPC protocol. Okay, so we have a direct relation between, also in terms of efficiency, between the MPC protocol that we choose and the zero knowledge protocol that we get. Okay, so let me briefly mention a few extensions. First is that because we open 2 views, we can in fact allow each pair of players to use any oracle, in particular an OT oracle, and we can check the consistency between the reported inputs and outputs of this oracle. So we can in fact use protocols, MPC protocols that are secure in the OT hybrid model, which we saw a simple example of such a protocol, even simpler than semi-honest BGW. We saw it in Benny's talk. This is the semi-honest version of the GMW protocol. We can also have a different variant of the construction that will not be compatible with the first extension, but if we don't have any OT oracle, then it's enough to use one secure MPC by just having not only commitments to the views, but also commitments to the messages exchanged on each of the channels between pairs of players. And then the verifier will open one view and one or all incident channels. We can also handle MPC with statistical error via some simple committed coin flipping protocol. But I think more interestingly, and I will not get into the details here, if we use an MPC protocol that uses a lot of players and is resilient against, say, a constant fraction of these players in the malicious model, then we can avoid the cost of soundness amplifications. Then we can get exponentially small soundness error directly without any amplification. And it's kind of interesting the type of constraints that this imposes on the MPC protocol. So in fact, things like broadcasts that are expensive in the context of MPC, they become cheap in this context because broadcast messages can just be directly sent from the prover to the verifier, right? So if we have an MPC protocol in this client-server model, in particular exactly the type of protocols that I described in the previous talk, we can apply them using a simple variant of the transformation I described before to get zero-knowledge protocols that have a similar efficiency, and again, they have a built-in, without any repetition, they get a good soundness. And finally, we can use standard techniques from the zero-knowledge literature to realize the ideal commitment with an actual commitment. Yes?
Maybe I'm missing something, but going back to the zero knowledge,
Mm-hmm.
doesn't always make sense to use 5 parties? Why do you say why not just say 5.
Right, so you have functionalities. This is, again, motivated by some applications. So first of all, if you care about concrete efficiency, you can use 3 parties in the OT hybrid model, or, I mean, it's not a priori clear which is better. But also, you have examples for MPC protocols for certain functionalities that have better asymptotic efficiency if you use a bigger number of parties. Right? You can think of low-degree polynomials. If you have more parties in the degree of the polynomial, then you can do it more efficiently than if you have fewer parties. So this was actually motivated by some concrete applications. Okay, so let me briefly mention these applications. First is kind of like conceptual simplicity, no magical, NP completeness results. It's kind of, nice to present to students this very surprising application of the theory of NP completeness to cryptography. But it's enough instead to learn the semi-honest BGW or GMW protocol. So if you teach a crypto class, it can make your job easier, especially if you also intend to teach. I'm not suggesting to replace it. It's beautiful the way it was originally done by GMW or the Hamiltonicity. It's very beautiful and elegant. But if you already know about BGW or GMW, there's a simpler way to do it conceptually. Okay, and again, we can use BGW. We can also use another protocol of Maurer that uses replication of additive shares instead of Shamir, which is, even a bit simpler than Shamir. Can use GMW, as I already mentioned. We can have another application, which is actually a variant of the protocol I described in the previous talk, combined with this use of algebraic geometric codes, in which the total communication complexity will be just a constant multiple of the circuit size of R, Boolean circuit size, plus low-order additive terms. Here it's just, there's no depth, it's just security parameter additive term. So it basically gives us something that, from an asymptotic point of view, looks very good compared to at least traditional zero-knowledge protocols. So this was when we came up with this result. This is, I didn't mention, this is joint work with Kushilevich, Ostrovsky, and Sahai. When we had these results, there were no, under any assumptions, and in any setting, there were no zero-knowledge protocols that have this complexity. So the best ones incur the multiplicative overhead of security parameter over the circuit size. Now we can use fully homomorphic encryption. You can either use directly fully homomorphic encryption, or you can use MPC based on fully homomorphic encryption and use the previous transformation. But now fully homomorphic encryption gives us an asymptotically better, so something like order of witness, right? You can't get below the witness size for proofs. Okay, so using fully homomorphic encryption, you can get it. Of course, the assumption will be much stronger, and practical efficiency will be much worse, and it will be only computational zero knowledge as opposed, even in the hybrid model, which is not that important. But I want to make two comments. One is that when you have when the circuit is shallow, then there is a better alternative now due to Goldwasser, Kalai, and Rothblum, which uses a different approach of interactive proofs, efficient interactive proofs, which doesn't work for general relations, but for shallow relations, it can reduce the size of the amount of communication to be some fixed small polynomial in the witness length as opposed to the size of the witness verification circuit. And finally, if you relax proofs to arguments, then you also have these theoretical and probably not yet very practical approaches based on PCPs that give us efficient arguments in which the communication complexity is just polylogarithmic regardless of the witness length. So that's basically a summary of the state of the art on the communication complexity of zero knowledge. But another nice thing is that sometimes people care about zero knowledge for some specific functions that arise in the real world. For instance, unfortunately for the authors, I've seen a submission to some conference that implements good zero knowledge protocols for linear algebra problems. For instance, you can think of a problem where you have say a matrix where some of the entries are public, and you want to prove that you know how to complete the remaining entries such that the determinant of the matrix is 3. Right? So this is a concrete zero knowledge problem that can be motivated by applications, and it turns out that there is a very rich line of work on efficient linear algebra in the context of secure computation, mainly in the case, but not only in the case of honest majority. And you can just use this transformation, apply this transformation to these protocols to get zero knowledge protocols with similar efficiency advantages. So if you want to think of good ways to do zero knowledge proofs for some particular relation, you can think of whether there are any tricks or known techniques that apply to similar functionalities in the multi-party setting. Even in the semi-honest model and even when there is honest majority. Okay, so this concludes the first example of applications of honest majority crypto. The second one applies to general two-party protocols, and this is joint work with Manoj Prabhakaran and Amit Sahai. And let's start by recalling again something that Benny covered on Sunday, the GMW paradigm. Now, the GMW paradigm, in retrospect, it looks, we take it for granted, but I think that it's really one of the most beautiful ideas that were introduced in cryptography. And, if you explain to people the idea of zero knowledge and how it's useful to take, a protocol that assumes that everybody behaves correctly and then makes it secure against arbitrary behavior, it's really a beautiful and very powerful concept. And again, as we saw, essentially modulo some or quite a few complications. The core idea is very simple. The core idea is to make parties prove in zero knowledge that they stick to the protocol, and the reason you need zero knowledge proofs is that sticking to the protocol involves some secret information that cannot be revealed. Okay, so this is a very influential and powerful paradigm, but from both a theoretical and practical point of view, a big disadvantage of this paradigm is that it's non-black box, in the sense that in the new protocol that you build, you need to have zero knowledge proofs for statements that depend on the code of pi. Right? So if pi will use AES, then we will need, even if pi is very efficient given AES, we will need to apply zero knowledge proofs to the computation of AES, which is very expensive. Or let me give you a more relevant example to Shai's talk. So even if Shai, Craig, and others manage to reduce the cost of fully homomorphic encryption to 1 second per gate, that maybe will make it more practical, then still, if you want to apply it in the malicious model, this is not something you should try at home, unless you have something very good to say about the structure of this function. So, more broadly, this is why the GMW compiler is typically considered as being impractical. And from a more theoretical point of view, the GMW paradigm does not apply even at the syntactic level to protocols that use an oracle, semi-honest protocols that use an oracle. Now, what kinds of oracle can we have in cryptography? We basically have 3 kinds of oracles I'm aware of, all of which are useful. One type of oracle is a functionality oracle. For instance, the OT oracle. So, Benny described an extremely simple protocol in the semi-honest model that uses an unconditionally secure protocol that uses an ideal OT oracle. Now, if you want to get a similar result in the malicious model, Killian's, it's half of Killian's PhD thesis. If you look at it, you try to read it, you will realize that it's not simple at all. And in particular, he could not apply the GMW paradigm that existed at the time to get this conversion from the semi-honest model to the malicious model because there is this oracle, and the GMW paradigm requires you, all information to be public, and it does not apply. Also, there is the fact that it uses computational assumptions, but the oracle poses a syntactic problem. Another type of oracle is an oracle to a crypto primitive, for instance, a pseudo-random generator or a symmetric encryption primitive. So in Yuda's talk, we saw yesterday that you need to spend a lot of effort to take Yao's protocol, which is very simple in the semi-honest model, and if you want to get a similar protocol in the malicious model that still makes a black box use of this cryptographic primitive, this is a highly non-trivial task, right? Which is again motivated also by practical efficiency. A third type of oracles that you might want to use is an arithmetic oracle, right? So you can, for instance, take a protocol in the semi-honest model that makes, the protocol is made much more efficient by the ability to multiply and add large numbers, right? This is, for instance, the case for things that are based on homomorphic encryption. Even if they become more efficient, if you take the somewhat version, you still need to do arithmetic computations on big numbers, right? Also in real-life computations involving numbers. So if you have this black box use of an arithmetic ring oracle, again, moving to the malicious setting will require you essentially to do bit-by-bit simulation of these arithmetic operations. So these are the 3 types of oracles that motivate us to try to find some black box alternative to the GMW that will relativize, that will also work when we have these oracles. So that's the motivation. And now, how much time do I have? Okay. I am not used to having more time than I need. This is a very... Actually, I think that the reason I'm getting invited to all these things is that people want to see if I can ever finish a talk on time. So now I might not get ever invited again to anything. Okay, so I was building on the International Congress of Mathematicians, but now it will not happen. So, okay, so anyway, the dream goal that we really would like to satisfy is the following. It would be extremely neat if we could take any protocol that realizes some functionality F in the semi-honest model. And so the point here, a crucial point, is that we don't have a description of F. We just have the protocol which implicitly gives us an oracle to F, but we don't have the description of F. We just have the protocol at hand. And now we want to build on top of it, using Oracle access to this semi-honest protocol, we want to build a protocol pi prime that realizes the same functionality F in the malicious model, right? This would be what everyone would agree that if I have something like this is a black box version of the GMW compiler, right? You can raise all sorts of objections later, but at this point I think we can all be in agreement that this is truly a black box version of the GMW compiler, and this is great. And in fact, in some cases, if we fix some functionalities F, for instance, oblivious transfer, then it's something we can actually do. You know, in a joint works with Kushilevitz, Lindell, and Petrank, and in a work of Heitner, we show that you can take any oblivious transfer protocol that is secure in the semi-honest model and use it as an oracle in a black box way with a black box proof of security to get OT in the malicious model. But if you try to be more ambitious and generalize this to general functionalities, it's easy to see that this is impossible. And the reason is that there are some, for instance, there are some functionalities like a zero-knowledge functionality which is trivial in the semi-honest model, right? In the semi-honest model, the prover just says, hey, trust me, it's true, right? It's semi-honest, so this works. This is a secure implementation of zero-knowledge in the semi-honest model, but in the malicious model, it doesn't work, and you can formalize this argument to show that this is impossible in general. So what I will present now, and this is the IPS compiler in the title of the talk, is what we view as the second best alternative to this dream goal. And the idea is not to make use of a single protocol as an oracle, but actually to make a black box use of two types of protocols. But both types of protocols are easier than what we're trying to get, right? So we're trying to get a two-party protocol with security in the malicious model. And to this end, we are willing to make a black box use of two types of protocols. The first is referred to as an outer protocol for a reason that will become clear later. Is a protocol that has to be secure against malicious parties, but it can have an honest majority. So you can think of a protocol like the ones from the previous talk that are quite simple, right? Especially if you don't consider this packing business, right? You can have a really simple protocol. You don't care even that the security threshold be optimal. You can have resilience to 10% of corrupted servers, and this is the outer protocol. This is one ingredient that we need. It's clearly easier than the end goal of getting a two-party protocol with security in the malicious model. The second building block is called an inner protocol, and this will be a protocol that is secure in the semi-honest model with two parties. And in addition, this protocol can use an oblivious transfer oracle, right? So other than having simple feasibility results in both of these easier models, both of these feasibility results can be unconditional. So we can have unconditional and composable, right? Universally composable. We can have unconditional and universally composable security with an honest majority. We can have unconditional and composable security in the semi-honest model. So these two settings also allow us to get, in these two settings, we can get stronger feasibility results. Okay, so a bit in more detail about these two building blocks. We have an outer protocol which is in the client-server model that I described before. So if our goal is to get a two-party protocol, then we have two clients. If we want a five-party protocol with security in the setting of no honest majority, we have 5 clients. And we will have K servers where K is a statistical security parameter. Okay, so if we want probability to the minus K, it will not be K servers, it will be some constant multiple of K. So to be more concrete about the requirements, we need security against malicious, adaptive adversary that can corrupt simultaneously one client and some constant fraction of the servers. We're not too picky about the constant. It's enough to have security with aborts. Right? We can't get fairness, for instance, in the final protocol anyhow. And we need, for technical reasons, we needed to have a UC-style simulator, so simulation should be done in a straight-line way, but this is all not a problem because all natural protocols in the honest majority setting have these features. In particular, we can call something I call BGW Lite, which is a much, much simpler version of BGW than what Benny described, which is simpler because we don't want optimal resilience and we don't need full security. Okay, the inner protocol is again a two-party protocol that can optionally use an OT oracle. And here we need security against semi-honest adversary only. And to make the analysis of the simulator simpler, it's helpful to assume that this protocol is adaptively secure but with erasures. Yes? Mm-hmm.
If any way you can abort, then do you gain anything by using t less than n/4 instead of n/3?
Well, you might gain a little bit by the concrete constants, but otherwise, no. You're asking if you gain something by using n/4 versus n/3?
If you use t less than n/4, you gain a lot in BGW, but if any way you can abort...
Yeah. So n/3, right. So yeah. If we want to get the simplest form of BGW for security with a board, then it seems like you can't make it any simpler by moving from n/3 to n/4. Yes, good point. Okay, so again, for the simplest version of the simulator, we want to assume this inner protocol to be adaptively secure, but allowing erasures, which is again an easy setting, and all natural two-party protocols can be easily made adaptively secure with erasures. Okay, and an example for this protocol is the GMW Lite, which is the two-party version of the semi-honest protocol that Benny described on Sunday. Okay, so now this is the critical slide. How do we combine these two protocols? So the idea is to use a more sophisticated flavor of server virtualization. At a high level, at an outer level, the two clients will run the outer protocol, but of course we don't have the servers. So how do we run the outer protocol? The idea is to use, again, this player virtualization technique to distribute the computation of each server between the two clients. Now, you can think of the server algorithm as, again, referring to Benny's talk from yesterday. He referred to reactive functionalities. Reactive functionalities are functionalities that can receive inputs and produce outputs in multiple rounds and carry some state information between rounds. So you can think of what a server does as realizing some reactive functionality. The inputs in each round are the messages that are coming from the clients. The outputs are the messages that are going back to the clients. And there is a state which is updated, but servers in natural protocols don't need to actually maintain a lot of state. So this is how it's done. But because, and this is the crucial additional idea, that because we only run a semi-honest secure protocol to virtualize each server, we need to employ some mechanism to make sure that these executions of the semi-honest protocol are done faithfully. And for this, we use something that is reminiscent of a cut-and-choose technique, except that it's done in a more seamless and automatic way. And the idea is to have something that we call a watch list or oblivious watch list, which allow each client to have a full view of the entire emulation of some constant fraction of the servers. So on the servers that are being watched, each client can catch any deviation done by the other client. Except that the other client doesn't know which servers are being watched, and so he cannot cheat on too many instances of the inner protocol, because then he will be caught with overwhelming probability. So, and this is done symmetrically, so each client will watch the other client. And there is also an issue of, if the inner protocol uses an OT oracle, you can't cheat and get away with it, right? Because we don't have any view of what you can report that you sent to the oracle one thing and in actuality sent to the oracle another thing. But this is easy to take care of by using this random self-reducibility of OT and ensuring that the inputs on which the OT oracle is invoked are random, and therefore lying on what you send to the OT oracle is risky. You will also get caught with constant probability. This is a technicality. But the main idea, and this is Alon suggested this analogy, there is this experimental type of prisons called the panopticon, where each prisoner has a cell that with some probability it's a one-way glass where they can be watched. There is one poor guard that can only see a small subset of the prisoners, except that they don't know when they're being watched, and therefore so this is kind of a similar idea. Okay, so let me just spell out in a bit more detail the syntax of this server virtualization, right? How do we emulate a server? So we can assume that the servers are deterministic. Again, these are just some simplifying assumptions. This is already the case for natural protocols like the one that I described in the previous talk, but it can be also enforced in general with a small overhead. Now, in the outer protocol, now this is just a more detailed definition of something I explained before. So if you look at the outer protocol, then server I realizes some reactive functionality that takes incoming messages from clients as inputs and produces outgoing messages to clients as outputs and can possibly update the state. Right, so this is syntactically just a reactive two-party functionality, and then the inner protocol will be a semi-honest secure protocol that realizes this reactive functionality. As Benny mentioned in the talk, you can reduce reactive functionalities to standard non-reactive functionalities. Yes?
You said something before that I don't understand. You said that it's black box both in the outer and inner protocol.
Yeah,
it's black box in the inner, but not in the outer. Here you're relating to the actual messages of the outer.
Right. So I will make a precise theorem statement. So again, I will make a precise theorem statement that exactly clarifies the rule of the game, and I will also address your question. So I will make a formal statement. Okay, let me answer now, and then so the inner protocol needs to realize a functionality that is defined by the outer protocol, right? This is the part that raises objection. Now, the crucial point from the point of view of formulating a theorem, the IPS theorem, is that this functionality is defined in a black box way from the protocol. So if you look at the protocol as an oracle that computes the next message function, you can actually define this reactive two-party functionality. If you have a factory, sealed implementation of the next message function of your protocol pi, you can use it, build on top of it in a fairly trivial way. Another box, you don't need to look at the code. So my point is the following. If you allowed the function, if I allowed, and you will see it in the final theorem statement, but if the outer protocol makes a black box use of the ring, then the functionality which we realize in the semi-honest model will also make a black box use of the ring.
But I need to know what the outer functionality exactly is. I need the code of the outer functionality, of the outer protocol.
No. So I'm saying that the formal theorem, again, there is no. So the crucial point that prevents the theorem from being trivial is that the functionality that is realized by the inner protocol is defined in a black box way with respect to the outer protocol. So it's kind of like, and I will discuss it in more generality, I will show a more general version of this black box game. So it's a black box game that involves 3 moves. You have a functionality, you have one move where you get a protocol, an outer protocol for this functionality, then you have another black box. This is a kind of given. Now you can use it as an oracle to build another functionality. This protocol is an oracle. Now you get a semi-honest protocol for this functionality, and you use both protocols in a black box way to get the final protocol. So again, it's not clear. I'm just saying that you can formulate, and I will formulate, a formal and concise theorem, and I challenge everyone to prove this theorem in some trivial way, you know, by using the GMW compiler. That's the point. That if you insist on the relation between the outer protocol and the functionality realized by the inner protocol being black box, then the statement becomes non-trivial. If you don't insist, if you just allow an arbitrary way of defining the inner functionality from the outer protocol, then indeed the theorem statements become trivial to satisfy. So again, the end result, I think the proof is in the pudding. If you have, if I prove these new theorems as an application of this approach, and I convince you that in some way it is black box, then I guess I'm entitled to call it black box, but I agree, it's a more controversial statement than the dream goal.
I can find this one last comment. I always understood it separately. The outer protocol is information theoretic, so I don't care. The inner protocol, which uses computational assumptions, that's where I care. So
no,
black box in the
so
I don't consider it black box in the outer protocol.
Yeah, so this is certainly true, but we want to apply it more generally even to outer protocols that are not information theoretic. I will mention applications later, but it's not always the case that the outer protocol is information theoretic. Okay, so essentially we have this reactive functionality that captures the role of every server in the outer protocol, and now we want a semi-honest secure inner protocol for this functionality. And this protocol will essentially distribute the state, again, as Benny saw, I mean, in terms of how these things are typically realized, you just distribute the state of the reactive functionality between the 2 clients. Okay, so now let me talk a little bit about this watchlist mechanism. So the motivation for using watchlists is that the inner protocol, because it is only semi-honest secure, it does not give us any way of preventing clients from sending bad messages in the inner protocol. Note that we don't care about messages that the clients send in the outer protocol, say to each other, because this is taken care of by the security of the outer protocol. The outer protocol is secure against malicious clients, so if the client cheats at the outer protocol level, this is not a problem. But when we try to virtualize a server using a semi-honest secure protocol, we'd better make sure that this semi-honest behavior is being followed. And now you can raise another objection that was a major theme in Benny's talk on the GMW compiler. How do we ensure? So just sending the right message is not everything. We also need, in general, to make sure that the players pick the randomness at random. There are 2 answers, or more than 2 answers to this, but one answer, the bottom line is that it's simple to deal with in our setting. For 2 reasons. Concrete reason is that you can define a notion of security that is stronger than semi-honest security, which basically says that security should hold even if the players use biased randomness. And if you look at natural protocols like the GMW protocol in the OT hybrid model, they already have these properties. So you can simulate it even if you choose bad randomness, so this is not a problem. The other question is that you can ensure this randomness either via a simple coin tossing procedure, very simple, unlike what Benny described, or you can even fix it at the semi-honest level. You can have a general transformation from a protocol that satisfies the standard notion of semi-honest security into a protocol that satisfies this stronger notion of semi-honest security that tolerates bad randomness. This is basically a triviality. I will not show it. So now the watchlist mechanism ensures that you can occasionally cheat, but you cannot cheat too often. In the sense that I cannot cheat in too many instances of the inner protocol. And this follows from the fact that each client doesn't know which instances of the inner protocol are being watched, and so we have this typical two-case analysis. Either you cheat a few times, in which case actually it should be T over 2 because we also have the servers that you're watching. So the servers that you're watching, you're watching, say, T over 2 servers, so this amounts to corrupting T over 2 servers, and now if you can cheat, now you can cheat additional T over 2 times, and overall it's as if you corrupted T servers in the outer protocol, and so the security of the outer protocol, again, the intuitive level takes care of it. Now if you try to cheat more than T times overall, then the security of the outer protocol gives you no guarantees. But then, by the choice of parameters, because T is a constant fraction of K, and each time you'll get caught with constant probability, then you will get caught with 2 to the minus omega of K probability. And again, this is not, a revolutionary new, technique. This is basically the good old cut and choose in a different setting. Okay, so let me be a bit more specific about how we implement the setup of the watch list. So the setup of the watch list, so the watch list will be basically at a high level. For each server, say that I'm a client A. For each server, I pick a long one-time pad Ri that is as long as all the information of the inner protocol in the I server. So take the randomness and the messages, everything combined. This will be the length of this one-time pad Ri. Now, if you settle for computational security, if you don't want unconditional security in the OT hybrid model, you can implement also, instead of using a long one-time pad, you can just use a seed to a pseudo-random generator. So it's not necessary for this to be long. Now I want to transfer each of these. So each of these Ri will be used to mask my internal information when simulating the ICE server. So I send all my internal information, all of my view of the ICE execution of the inner protocol, I send it masked by this Ri, and now we just need to guarantee that you will receive each Ri with some small constant probability. So I want roughly to deliver to you, I don't want, but the protocol wants to force me to deliver to you roughly T over 2 of these Ri's without me knowing which. So you can think of several ways of implementing it. It's essentially, M choose N oblivious transfer, again related to something to the cut and choose oblivious transfer that Yuda mentioned. But in this case, it turns out that at least from an asymptotic point of view, what we need or what we can use is what is known as Rabin OT. So instead of ensuring that you receive a precise number of these strings, I can just transmit to you each string with independent success probability P. And this is exactly Rabin oblivious transfer. It's like an erasure channel. I send you this Ri, and with probability P you get it. With probability 1 minus P you don't get it, and you know that you don't get it. And I don't know which is the case. And it turns out that if this P is, we also care about in the applications about asymptotic overhead. So if you choose P to be a rational number, not 1 over pi, but say 3/15, then you can actually implement this perfectly with a constant number of instances of 1 out of 2 string OT. Right? So there is an explicit protocol that achieves it with full security in the malicious model, UC security, whatever you want. Okay, and this ensures me, so this is some approximation. Ideally, we could have full control of the number of servers that you watch, but by Chernoff bound, this guarantees that we have a good approximation of the number of servers that you watch, which is good enough. So now, how do we use the watch list? So again, this just repeats what I mentioned. Whenever I do it in an online fashion, whenever I gather some new information, a new message I should send, or something new that happens in the inner protocol, then I just report it over the ith watch list by masking this new information with this one-time pad RI. And so if you obtain RI, you have a full view of what I report in the inner protocol, which together with your view, basically, I mean, you are able, using this full view, to check whether I send something wrong in the inner protocol. And as soon as you detect that I cheat, you abort. And again, repeating something I already said, if we have ideal OT calls in the inner protocol, we can make sure that these calls are risky and they will be caught with probability 1/2, but let's ignore this in the following. So just to give you an example of how this works, if you look at the previous talk, if you look at this MPC protocol I described is precisely of the type that we need in the inner protocol, modulo adaptive corruption, which is also fine, except that it requires a slightly more involved analysis, especially if you want to get it efficiently. So in this protocol, we have each server performing 2 types of computations. And now I'm specializing it to the two-client case, but it's similar in the case of a bigger number of clients. So one type of computation is to basically do something known as oblivious polynomial evaluation. So the local computation takes value AI from client A, and values BI and ZI that are received from client B, and delivers this polynomial. So one party holds a degree 1 polynomial, the other party holds a point, and the guy who has the point gets the output. So this is kind of like an arithmetic generalization of oblivious transfer. This is a very simple computation that can be implemented efficiently. And by the way, the number of such computations is just a constant in the protocols that I showed. Overall, if you sum the number of such computations over all servers, it will just be a constant multiple of the circuit size. And now you can ask, how do we get, and now we need to implement this type of computation in the semi-honest two-party model, and you can ask, and it's a very good question, how do we do it? So because we are dealing with a semi-honest model, there turn out to be several good methods of doing it. One is by making a black box use of a standard homomorphic encryption such as PAIE. If the domain size, if the field is small, you can use a variety of other things, El Gamal or Goldosser Mikali or other things. But again, we can use any homomorphic encryption. PAIE has some technicality in that it's not over a field, but over a pseudo field, but in the semi-honest model, it's very easy to take care of all these technicalities and get a secure realization making a black box use of any homomorphic encryption, things get more complicated only in the malicious model. Other alternatives for implementing this computation in the two-party semi-honest model include we can get an unconditional, if we allow the inner protocol to use an OT oracle, we can get unconditional implementations either using the GMW, which can be annoying because we need to emulate this, even if the field has just n+1 elements, we need to basically emulate a Boolean circuit that computes this multiplication, which can be costly. So this is a good motivation for using algebraic geometry codes. Maybe this can, make the computation cheap even when you have a Boolean GMW style protocol. But you can even do it more efficiently using just even a black box access to the field or any ring, right? So you can do it in a better way. Another and even more efficient way of implementing this inner protocol is using all kinds of assumptions about intractability of decoding certain linear code with certain levels of noise. So you can use Reed-Solomon codes as suggested by Naor and Pinkas in a paper on oblivious polynomial evaluation. And you can use even random linear codes, which are harder to decode. So Reed-Solomon codes are easy to decode from with some level of noise, but beyond a certain level of noise, even when we have enough information to distinguish between a noisy code word and a completely random vector, it's conjectured to be hard to distinguish between the two. So we actually have a variety of different implementations that may be incomparable in practice or depend on the particular scenario. Now, and the reason I'm spending so much time on this is that this is essentially the only non-trivial computation that is done by typical outer protocols from the literature. So we'd better do it efficiently. This is the thing that's repeated all over again. Now, another type of computations that the server did was to compute all kinds of linear combinations. But these linear combinations were always done on values that are known entirely to one of the clients, right? So we have had this verifiable secret sharing procedure where I send a bunch of field elements to each server, and now there is some public linear combination, and this server is supposed to broadcast to everyone or to send to another client this linear computation on the clients. Now, because it's a reactive functionality, and because I know all the values that I sent, I can locally compute it and still realize the notion of security in the semi-honest model. Again, so in the semi-honest model, values that I know, I can compute on them for free. There is no need to employ any kind of secure computation machinery for this. And this is actually very crucial even from an asymptotic point of view, because while the number of these multiplications is only a constant multiple of the circuit size, if you look at the exact complexity, so this is like a constant overhead. If you also count these local operations, you will already get at least a logarithmic overhead. So the fact that these operations can be done locally means that we don't need to pay this logarithmic overhead in communication. We will only need to pay it in computation. And again, this example will give us efficient, at least in an asymptotic sense, protocols for arithmetic or Boolean computations as a special case. So, simulators in this setting are always tricky. I refer you for nice pictures to a preliminary full version that's on Manoj's webpage. But the high-level idea is similar to the type of simulation that is used in composition theorems. We basically let the outer simulator interact with the inner simulator. The outer simulator does a bunch of things, but it basically generates virtual messages to the servers. These are not messages that need to be simulated, but these messages are used as inputs and outputs to the inner protocol, which now the inner protocol can take and generate the real messages that happen in the protocol. Now, naturally there is a lot going on, but the main point I want to say here about the simulation, which also illustrates why we need the outer protocol to be adaptively secure, the point is that the simulator can see when a client cheats in an instance of the inner protocol. And in such a case, the inner simulator is worthless, because the inner simulator can be used as long as we follow the inner protocol. Once we deviate from the inner protocol, we can no longer use the inner simulator. It provides us no guarantee. And then what we do is we make the outer simulator corrupt the corresponding server. And once it corrupts the corresponding server, it has the full information about the inner protocol, and it can continue the simulation. Okay, so, and this is why corruptions can be adaptive, because I can decide that at one point I cheat on one server, and on another point I cheat on another server. And what the simulator will do is, there is a more elegant, so this version works when there is no OT, there is a more general way of making it work in general, but you can think of a simulator, the main simulator, when it observes that a client cheats on the ICE watch list, it will make the outer simulator corrupt the ICE server and will flip a coin with probability P that corresponds to this watch list reception probability, and if this coin turns heads, the simulator can abort. This corresponds to the event that I was unlucky and the cheating attempt was caught, and in which case the simulation can abort. Okay, so now I finally get to the theorem statement, and again, it's a bit tricky to formulate theorems in this domain, because there might be some trivial way. I mean, you can, if you're a bit careless in how you formulate the theorem, it might be trivial to satisfy. And again, it's in my lengthy response to Yuda before, I tried to convey this point. So anyway, the main theorem here is the following: given a two-party functionality F, if you give me an honest majority secure outer protocol for F, and a semi-honest secure inner protocol, possibly in the OT hybrid model, for a two-party functionality that corresponds to the server's program in Pi, and here I'm being a bit loose, I will tighten it later, and the point here is that this functionality G to the Pi, it makes an oracle use of Pi. So formally a protocol is just a next message function. This is some functionality that makes a black box use of this outer protocol functionality. And now, using these two ingredients as a black box, we get a two-party protocol in the OT hybrid model that realizes our initial functionality F with security in the malicious model. Okay, and this is an unconditional result. It's a kind of a black box style result. It does not rely on any assumptions. In particular, both protocols can be unconditional. They can also be computational. Okay, and the same theorem holds for in the M party case, the M client case. Okay, so let me quickly go over applications. I have 10 more minutes. So again, the first application is kind of like a cute way of revisiting the classics. In some sense, Killian's result at least modulo the details of proving our theorem, but Killian's result, which was a major effort, if you look at his thesis, it's really a major effort. It's essentially, not essentially, it can be, with much better efficiency, it can be obtained by just plugging in together BGW light and GMW light, each of which is very simple. Okay, so it's a conceptually simple combination. Also, the proof is shorter, but conceptually it's very simple. Now, let me talk a little bit about efficiency. Actually, this was our initial motivation. So initially, we were trying to understand Killian's, or get a simpler alternative to Killian, and to get a paper into crypto, we knew that we need to present some efficiency advantage. So we thought of getting that just giving a simple proof of a known result will not be enough, so we're trying to get also an efficiency advantage. And indeed, with all the known machinery in the honest majority MPC world, we knew that, so what you can get if you use a combination of the protocol, a version of the protocol I described in the previous talk that is based on these algebraic geometric codes, then you can actually get a version of Killian's protocol where the communication complexity is just a constant multiple of the circuit size independently of the level of security up to these additive terms. And also this protocol has a nice feature that is also enjoyed by at least one of the very recent protocols that Yuda described, but it has the feature that even if you now don't want to be in the OT hybrid model, you want to implement it in a computational, using a computationally secure protocol, then because OTs can be preprocessed, all of the crypto is done in the offline stage, and in the online stage, you just basically run the outer protocol concatenated with some inner protocol that you have several options to choose, but they can all be unconditional. Another nice thing that is related to the cut and choose Yao version that Yuda described yesterday is that we can get a multi-party version of the feasibility results. So if you want to get constant round protocols that only make a black box use of a crypto, say of a pseudo-random generator, so in the previous talk I just mentioned a result like this in the honest majority setting. And it turns out that with a little bit of work, you can get also, you can use this outer protocol and an unconditional inner protocol to get a similar result in the OT hybrid model. So it basically shows a feasibility, a black box feasibility result that if you have an ideal OT, then you can do multi-party computation in a constant number of rounds by just making a black box use of a pseudo-random generator, which again is not implied by the GMW compiler. It's true, it was known, you know, like the dishonest majority version of Beaver Mikali Rogaway that Benny mentioned achieved something like this in the semi-honest model, but it was open in the malicious model. And again, in terms of efficiency, I don't make any claims. In particular, I said that the efficiency of this outer protocol in the honest majority setting, here I can say with absolute certainty that the protocol that Yuda described yesterday is more efficient if you specialize this thing to the two-party case. But in the multi-party case, it's not completely clear how to generalize what Yuda described, whereas here it's a kind of a smooth generalization. Another nice thing is that we kind of base secure computation of OTs, but we can use this to generate OTs. What do I mean? So Benny mentioned yesterday a very practical protocol for extending OTs, you know, joint work with Killian, Nissim, and Petrank, which, you know, it's very efficient in the semi-honest model in a very practical sense. But now, if you have an inner protocol that uses a lot of OTs, what the IPS compiler tells you that you can use a semi-honest implementation of these OTs, and now you can apply the OT extension in the semi-honest model. So the end result is that we can get, and again, this is an asymptotic statement, but if you use the right inner protocol and outer protocol, you can get an OT extension protocol such that following an initial set of OTs, each additional OT will require just a constant number of applications of a suitable hash function or encryption scheme. So at least from an asymptotic point of view, it means that we have a constant overhead of getting security. So the initial paper with Kobe and others, we had this cut and choose overhead of statistical security parameter. We can reduce it asymptotically to a constant, but again, I'm not claiming practicality, but I'm just suggesting that this OT extension might even be practical in the malicious model. Again, modulo checking all the numbers, which is a daunting task. Okay, we have some other nice things. For instance, we can take any semi-honest OT protocol and use it asymptotically. If we can use it in a black box way to get malicious OTs with a constant production rate. So starting from a certain point, we will only pay a constant number of invocations of each semi-honest OT. So this is like a more efficient version of the result I described, the black box feasibility result that I described earlier. We can get constant rate OT combiners in the malicious model. We can get secure arithmetic computation over black box fields or rings. So if you have some algebraic structures, say you want to do a two-party computation of an arithmetic circuit over a big field, the traditional approach would be to either use, so again, a naive approach would be to just implement this field operation using a Boolean circuit and then use existing protocols. But using these unconditional inner protocols that I described in an earlier slide, combined with outer MPC, which do make, all outer MPC protocols do make a black box use of the underlying field and can be generalized to our general rings. Then we can get in the OT hybrid model, we can get protocols that make a black box use of the underlying ring. And we can also implement the OT, and then, we can make still a black box use of the rings and the OT. Now, if we implement, say that we know the ring and we have a concrete homomorphic encryption, so let's first ignore the fully. Think of pi. Say that you want to do arithmetic computation, so you want to do secure two-party computation of an arithmetic circuit over a big domain, and you want to use it by only black box use of the operations of pi. So these operations include key generation, encryption, decryption, and the adding or re-randomizing, whatever, the basic toolbox of homomorphic encryption. You can do it because the outer protocol can do arithmetic computation with no use of crypto, and the inner protocol only requires a black box use of crypto. And there are several technicalities. If you try to do it in an ad hoc way, you will encounter quite a few technicalities that are completely non-trivial, like generating keys in the right way. You can try to design special purpose zero-knowledge proofs to make sure that this modulus n is generated correctly. You have all sorts of technicalities that are all handled seamlessly by the fact that we only need a semi-honest secure inner protocol, and so key generation. And again, we don't need to distribute the key generation. The watchlist take care of it. You just send your randomness. Okay, and let me conclude with, because I'm now living up to my reputation and running out of time. So let me conclude that this is to the attention of the International Congress of Mathematicians. It's like the joke in Eretz Nehederet about Amos Oz. So, both of the instances of these black box games can be generalized into some kind of a black box game that has two kinds of move. A protocol move, which says, given an oracle, give me a protocol that realizes this functionality. A build move where we take an oracle and build another oracle, and now we want to iterate these two kinds of black box moves to move from one MPC model or two MPC models to a much stronger model. So this gives a formal sense in which we can try to argue about moving in a black box way from weaker notions of security to stronger notions of security, and the two results can be shown as two instances of this general game which restrict the sequence of moves. So finding other interesting instances is a nice problem. Finally, finding linear versions of the new compiler, in particular maybe relaxing the requirement on the outer protocol, and checking the practical relevance of all this are interesting questions with a lot of avenues for future work. So thank you. So let's thank the organizers.
Okay. Before concluding this winter school, I would like to give some concluding remarks. First of all, don't forget to return your feedback sheets so we'll be able to improve the program or improve the the planning of the next winter school, the next event if we're going to have one. I would like to give some thanks. First to the financial support that we received. We got a generous support from IBM and also from Bar-Ilan University, from the Department of Computer Science, the Faculty of Exact Sciences, and the Research Authority. I would like also to thank the guest lecturers, Shai Levi and Yuval Ishai, who invested a lot in preparing the long lectures they gave us today. I would also like to thank Yonit Homburger, who's not here, but I guess all of you met her, and she invested a lot of time in preparing this workshop and handling many issues that made it much more convenient for all of us. And last but not least, I would like to thank all the participants who came here, both from Israel and from other parts of the world. And we're happy to have you here. We wish you all a pleasant stay in Israel, if it's either short or long, and a safe trip back home. If you have any issues or problems during your stay in Israel, you have our cellular phone numbers on the invitation letters that you received, and you can call us if you need some help. And that's all, and I hope to see you in other happy crypto events. Thank you.